Today we are going to start to deal with the problem of finding normal modes of vibration of a rod. Actually, in case of rod, there may be two types of vibration: longitudinal vibration and transverse vibration. But here we will see only the normal modes of longitudinal vibration of a rod. So I have mentioned in this heading, this is just the longitudinal vibration of rod. Rod means a metallic rod, a solid metallic rod. In fact, this will be a very long concept, so I will divide this lecture in two parts. In this first part of the lecture on longitudinal vibration of rod, we will not see the calculation of normal modes. We will only see how we can write the equations of motion when the rod vibrates longitudinally. Okay? And after this lecture, we will continue to deal with the problem of finding the normal modes of longitudinal vibration of this rod. So let us see how we can write the equation of motion of a vibrating rod, which is actually vibrating longitudinally. Let us see for this figure. Actually, in this figure, I have shown a cylindrical rod. You can see this PQ is a metallic cylindrical rod. And this rod has been assumed to be of uniform cross section. It means cross sectional area of this rod is everywhere same. Okay? And you can also see that this rod has been placed along the x-axis. It means the axis of this rod is along x-axis. Okay? Now, when this rod, you can see in the first figure that here no external force has been exerted on this rod to vibrate it. So this is actually the equilibrium state of this rod. Okay? But now let us consider that an external agent struck this rod at its two ends. Let us say at P and Q. I am showing this by this arrowhead. Let us consider by two hammers. If you struck the two ends of the rod, or you may also struck only one end. There is no need to struck the another end. You may struck the rod at one of the ends. Let us say at this P by a hammer. And this striking is along the length of the rod. When this rod will be struck by a hammer along its length, or you can say lengthwise, then actually a longitudinal vibration of the particles of the rod will start. It means the particle will vibrate along the line of action of the force, that is along the length of the rod. In fact, it is found that this vibration takes place with frequencies of audible range. It means in this case a sound wave will be produced and that will travel along this rod. But that is the subject matter of our next chapter. Here we are not talking about wave. Okay? Now, as I have told you that in this present lecture our aim is to find only the equation of motion. But our prime aim or prime problem is what? Our prime problem is to find the frequencies of the normal modes of vibration of the rod. Okay? But for finding the frequencies of normal modes of the vibration of rod, we must first of all obtain the equation of motion of the particles of the rod. And so in this first lecture on this longitudinal vibration of rod, we will see only how to write the equation of motion. And from that equation of motion, again you will find a very important formula. which will be just identical to the result as we have seen in case of vibration of a string. Okay. Now let us see how we can find the equation of motion. And as I have told you that this rod is lying along the x-axis, and this figure 1 represents its equilibrium state, and this figure 2 represents the situation actually when this rod has been struck lengthwise. Okay, this is, and so the rod is get disturbed or perturbed. So this second figure actually represents the disturbed state or perturbed state of this rod. Okay. Now let us see. We for calculation we consider that our rod is composed of, it is made up of a large number of thin slices or thin elements. You may consider, and among those large number of slices in this figure I have shown only one slice, and this is AB, or you may say that we consider a thin slice, although in figure it appears very thick, but in actual sense it is very thin. So between two sections or cross sections A and B, you can see the first figure, I have considered a slice, and these dots actually represent the particles of this rod. Okay, and we consider that with respect to an arbitrary origin, let us say that this is our origin for calculation. The x coordinate of section A is x1 and that of section B is x2. So in undisturbed condition, what will be the length of the element which we have taken under consideration? That length will be simply equal to x2 minus x1, which we consider as delta x. Okay, so this delta x, which is x2 minus x1, that is the original length or the undisturbed length of the element AB. Okay, but when you will exert a force longitudinally, then actually the particles of the rod get displaced. We have shown in this figure that the particles at this end A, okay, this end A has been displaced to A dash. You can see this figure, it is displaced to A dash. This is the position of A, okay, and this has been displaced to A dash. Okay, and the particles at position B are displaced to this B dash. Okay, in fact we consider that the displacement of the particle at section A, that is at x equal to x, this is equal to y of x1. This y of x1, as you can see in this figure here, I have assumed that this is displacement of section A. Okay, so the coordinate of this point A dash will be what? That will be x1 plus this displacement. This displacement is this much, this is A dash. So its x coordinate is x1 plus y of x1. Here y has been assumed for displacement, and this y has a value y of x1 for the section A. Okay. Similarly, you can assume that the particles at the section B are get displaced by y of x2. So now the x coordinate of the displaced position B dash will be equal to x2 plus y of x2. Okay. Actually, all these things I have mentioned here, you can see that we have assumed that this x1 is the x coordinate of section A in undisturbed condition, and x2 which is actually equal to x plus delta x, that is the x coordinate of section B. Okay. So in undisturbed state, length of the section AB or the element AB, you can say, that will be equal to x2 minus x1, which will be delta x. Okay. But as I have told you, when this rod is struck lengthwise, okay, then section A is displaced to A dash and B is displaced to B dash. And as I have told you that we assume y is the displacement along x-axis. But this displacement will be different at different section. So displacement of the particles at the section A is y of x1 and displacement of the particles at section B is y of x2. Okay. So now the element AB in a disturbed state or perturbed state becomes A dashed B dashed. A dash B dash. Now you can easily find what will be the length of this element A dashed B dashed now. For this we will subtract the coordinate x coordinate of point A dashed from the x coordinate of point B dash. So you can see this A dashed B dashed, this will be equal to what? A dashed B dashed will be equal to x2 plus y of x2 minus x1 plus y of x1. And this can be written as y of x2 minus y of x1 plus x2 minus x1. But you know x2 minus x1 is this delta x. But you know the original length or the undisturbed length of the element AB was delta x. So when the rod is not vibrating, then length of the element AB is delta x, and when the rod is vibrating longitudinally, then this element becomes A dashed B dashed and its length is this much. So definitely there will be a change in length of the element, and you can now easily find the change in length. Actually, as I have told you earlier, that in this lecture we are going to find the equation of motion. And how you will find the equation of motion? Actually, we will find the force acting on this element AB by two methods. First of all, we will find the force acting on it by the concept of elasticity. Okay? And after that, we will find the same force in terms of Newton's second law of motion. And after equating those two equations, you will get the equation of motion. Okay? And so, if your aim is to find the net force acting on that element, for getting that force, you have to find the stress acting on the element. And for finding the stress, you have to find the value of strain. And for finding the value of strain, you have to find the change in length. Therefore, here I am first of all calculating the change in length of the element AB. That will be simply equal to A dashed B dashed minus AB. That will be actually the change in length. But you have seen that A dashed B dashed is equal to this much, okay? And AB is equal to this much delta x. So this will be y of x2 minus y of x1 plus delta x minus delta. Now this delta x will cancel out, and therefore change in length of the element AB will be simply equal to y of x2 minus y of x1. As you have seen in my lecture on the vibration of a string, that we can find the value of this y of x2 minus y of x1 by using the idea of Taylor's expansion. You know, in accordance with Taylor expansion, y of x2 is given as y of x1 plus del y by del x at x equal to x1 times x2 minus x1. x2 minus x1. But instead of x2 minus x1, I have written delta x. Okay? And then plus 1 over del 2y by del x square at x equal to x1 times x2 minus x1 whole square. For that I have written delta x square and the higher order term. But if you are considering the case of a small oscillation, a small vibration, then this delta x must be very small. So let us consider the case of a small oscillation, and in that very case this delta x will be very small, negligibly small. So the terms containing delta x square, delta x cube and other higher power on delta x, those terms will be negligibly small, and you may neglect those terms in accordance with our first approximation. So using the idea of first approximation, that is neglecting the higher order terms, you can see this y of x2 will be simply equal to y of x1 plus del y by del x at x equal to x1 times delta x. And therefore y of x2 minus y of x1, that is simply equal to delta x times del y by del x at x equal to x1. Okay? Now actually we will substitute this value of y of x2 minus y of x1 in equation 1 for getting the value of change in length of the element. Okay? So now you can easily see the change in length of the slice AB is equal to this much. Okay? Now after getting the value of change in length, you can find what strain will be produced in this slice. That is called longitudinal strain, and you have definitely an idea of a stress and a strain because you have studied the course on elasticity on your lower classes. So longitudinal strain, if you denote it by the symbol epsilon, what will be its value at x equal to x1? This is given as epsilon of x1, and this, in accordance with the definition of a strain, longitudinal strain, this is simply change in length divided by original length. But in this equation 2 you have obtained the value of change in length. So let us substitute this value of change in length here and divide it by the original length of that slice. What is its original length? Can you say? You can easily say that this is simply delta x. Okay. So now this delta x and this delta x will cancel out, and the longitudinal strain epsilon of x1, this is equal to del y by del x at x equal to x1. Okay. Now after getting the value of a strain, we can now find the stress acting on that element. And for this we consider that this capital Y is the Young's modulus of the material of the rod. Okay? And we also consider that this S of x1, this is a stress acting on the element at x equal to x1. Then you know Young's modulus is simply longitudinal stress by longitudinal strain. So Y will be given by S of x1 divided by epsilon of x1. And therefore, this S is equal to Y times epsilon. Okay? But you have seen that this epsilon, which is longitudinal strain, that is equal to del Y by del x at x equal to x1. I have written only x1, that means x equal to x1. Okay? So in this way, in terms of the Young modulus of the material of the rod, we have calculated the value of stress acting at this section x1. This section x1, we have calculated actually the strain at x equal to x1. Now in the similar manner, you can easily find the value of stress acting at the section at x equal to x2. For this, see this equation, and you can write that stress at x equal to x2 is S of x2, and on the basis of that result we can say that this is y times del y by del x at x equal to x2. Okay. So now as you can see that this is our element, let us say this is our element, this is A dash section and this is B dash section. Now this stress S of x2 is acting in this direction and S of x1 in this direction. Okay. So what is the net stress acting on this element? This will be simply Sx2 minus Sx1. And after putting the values of S at x1 and x2 from equation 4 and 5, you can see this will be y times del y by del x at x equal to x2 minus del y by del x at x equal to x1. Now we consider that this del y by del x is equal to f of x. So what will be this del y by del x at x equal to x2? This can be written as f at x2. And del y by del x at x equal to x1 can be written as f at x1. But again, you know from the Taylor's expansion that f at x2 minus f at x1. Just you have find here by Taylor expansion the value of y of x2 minus y of x1 which is this much. So in the light of this result on using Taylor expansion in case of first approximation, you can say that this f of x2 minus f of x1 is simply equal to del f by del x times delta x. Okay, I think you have got at the things because you have already learned this thing just now. Therefore, now let us substitute this value of f of x2 minus f of x1 here. And so s at x2 minus s at x1 is equal to this much. This is capital Y, which is actually Young's modulus times del f by del x times delta x. But you can see this f is here, you can see f is equal to del y by del x. F is equal to del y by del x. So instead of f, you may write del y by del x. Okay. So s at x2 minus s at x1, this will be equal to capital Y, which is actually Young's modulus, that is equal to del 2y by del x square times delta x. Okay. So in this way, we have obtained the value of the net stress acting on the element AB under our consideration. Now, you can easily find what will be the net force. You can see my previous figure that this is the displaced position A dashed and B dashed. And I have shown in the figure earlier that the force acting on this section A dashed is F at x1 and that on B dashed is F at x2. Okay. So the net force acting on this element A dashed B dashed will be what? That will be equal to F at x2 minus F at x1. Okay. And so the net longitudinal force acting on this element is given by this much. But you know, this force is simply equal to stress times cross-sectional area, because stress is defined as this thrust F divided by the cross-sectional area. So F is A times S. Okay. And we have assumed in the beginning that our rod has the cross-sectional area A and its cross-section is uniform. So everywhere, both at x equal to x1 and x equal to x2, cross-sectional area is same. And therefore, F at x2 will be equal to A times S at x2, and F at x1, this will be A times S at x1. Now let us take this A as a common factor. So F is equal to A times S at x2 minus S at x1. Okay? But we have already calculated in this equation 6, you can see the value of S at x2 minus S at x1. So let us put this value here, and after putting this, you get F equal to this much. This is the net longitudinal force acting on the element or the vibrating element, you can see. So in this way, using the idea of Young's modulus of elasticity, you can see we have calculated the net force acting on the element AB. Now, this force can be also calculated by using Newton's second law of motion. Okay, you know, if we make a free body diagram, this is your element, and let us consider that mass of this element is delta m, and the net force acting on it is F. Then you know, according to Newton's second law of motion, this F will be equal to delta m times acceleration. Okay, but as this element suffers displacement y in x direction, displacement is y, but it is suffering in x direction. So this will be equal to delta m times del 2y by del t square. Again, you can mark here that I have taken the partial derivative, not the ordinary derivative. Why? Because actually in general this displacement y will depend on two independent variables. One will be x and another will be t. But for getting the value of acceleration, you will have to differentiate this y 2 times with respect to t, keeping x constant. So I have taken partial derivative. So in accordance with Newton's second law of motion, you can write that F is equal to mass times acceleration. Now, what will be the mass of this element? Mass, you know, this is simply equal to volume times density. So if you assume that rho is the density of this rod and V is its volume, then this will be V into rho. But what will be V? V is area of cross section times length. Length is delta x. A is area of cross section. So A into delta x is its volume, and times density, that will be mass. So at the place of mass, you can see here I have written rho A times delta x. This is mass of the element, and times del 2y by del t square. What is this? This is acceleration. So in accordance with Newton's second law of motion, the same force F acting on the element can be written by this expression. So this is not any new force. This is this elastic force. Okay, but I have written the value of this F by another technique, by applying the Newton's second law of motion. So now you can equate equations 7 and 8, and when you will equate it, you can see this will be rho A times delta x times del 2y by del t square equal to capital Y A times delta x del 2y by del x square. Now here this A times delta x will cancel out, and therefore you can see del 2y by del t square is equal to y over rho times del 2y by del x square. You can, where I have actually assumed here V equal to root over y by rho. So y by rho can be written as V square. In fact, if you will check, you will find that the dimensions of this quantity V will be just the dimensions of velocity. Okay? Actually, here we will not say that it is velocity, but here we will only say that this is a constant factor here. But you have already studied earlier in my previous videos the classical wave equation. If you will remember the classical wave equation in one dimension, you can see this equation is nothing. This is simply the classical wave equation. Okay? And in that case, this v is called wave velocity or phase velocity. So I have told in the first lecture, that is in introductory lecture of this chapter, that when you talk about continuous media, the problem of continuous media, that switches to the concept of wave. So this idea leads to the concept of wave. Actually, when we struck the rod longitudinally, then sound wave is produced, and that sound wave travels through this rod with this velocity v. But that is the subject matter of our next chapter. Here I am not talking about that. Okay? So this result is exactly same as that we have studied in case of the vibration of a string, where v was equal to T over mu. Instead of Young modulus, here there was tension T, and at the place of density there was linear mass density mu. But one difference is here, that here we are considering the longitudinal vibration of the rod, but in that problem we have considered the transverse vibration of the string. Okay? As I have told you that actually when we will study about wave in the next chapter, then we shall learn that when a rod is struck lengthwise, a sound wave travels in the rod with a velocity which is given by this result. This is the subject matter of our forthcoming videos on the wave. Okay? And as the wave travels along the rod, different particles acquire displacement y of xt. Okay? Y of xt, which is a function of both x and t. Okay? Actually, it may be remarked that the picture presented in this video is crude one, because the particles of the rod has bouncing back and forth due to thermal agitation, even when there is no sound. Okay? So the quantity y of xt actually measures the average displacement, not the instantaneous displacement, due to the sound wave of those particles whose average position was originally at x. Okay? But this is the subject matter of our forthcoming videos, when we will start to learn about the concept of wave. Okay? So I think definitely this session was useful to you. Now, in continuation of this lecture, in our next lecture we will see the same problem for finding the normal modes of the longitudinal vibration of a string. Okay? Thank you very much.